How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You're holding your phone. It feels solid, cool, inert, a single object. You tap the screen and in an instant, it recognizes your face, unlocks, and presents a vibrant world of information. You scroll through photos, memories rendered in perfect clarity. You ask it a question, and the collected knowledge of humanity is sifted and delivered to you in seconds. It feels effortless. It feels like magic. We tend to think this magic lies in the software, in the code. We imagine the intelligence of our devices as something abstract, floating in a digital cloud. But that's not the whole story. The foundation of that world isn't abstract at all. It's intensely physical. It lives on a tiny sliver of silicon, no bigger than your thumbnail, packed with billions of microscopic switches. We call it a microchip. The common assumption, if we think about it at all, is that these chips are printed in some advanced way, like a microscopic newspaper. But how does this actually work? What simple rules make it possible to build structures so small they are invisible to the naked eye, yet so numerous they rival the number of stars in our galaxy? Today on First Principles, we're opening the black box on what is arguably the most complex and precise manufacturing process in human history: how microchips are actually made. The experience of modern technology is one of seamlessness. It's the instant response of a touchscreen, the immediate clarity of a high-resolution video call, the uncanny intelligence of an app that suggests the perfect route through traffic. We've become so accustomed to this effortless power that we forget to be astonished by it. The device in your pocket is not just a phone, it is a supercomputer. A supercomputer that would have filled an entire room and cost millions of dollars just a couple of decades ago, now sits comfortably in your palm. This incredible leap in power is famously described by Moore's law, the observation that the number of transistors on a microchip doubles roughly every 2 years. We hear that phrase and maybe picture a line going up on a graph. But what it describes is a physical reality that is almost impossible to comprehend. Imagine a city. In 1970, that city had a population of a few thousand people. Now imagine that same city, the same physical area, holding the entire population of planet Earth. That is the kind of density we are talking about. But instead of people, we're talking about transistors, tiny electrical switches that are the fundamental building blocks of all computation. A modern chip, like the one powering your smartphone or laptop, can have over 100 billion of these transistors. Each one is a physical object, with gates and channels and wires, built in a complex three-dimensional structure. And each one has to be perfect. If even a small fraction of them are flawed, the entire chip, the brain of the device, fails. This isn't just about making things small. It's about making billions of things small, connecting them all perfectly, and doing it millions of times over on an assembly line. The miracle we see is the effortless performance. The magic we feel is the speed and intelligence. But the real story, the deeper magic, is in the manufacturing. How do you build a city with 100 billion buildings, where each building is smaller than a virus, and do it on a piece of silicon the size of a postage stamp? To understand that, we have to go back to a time when computers were anything but small. Before the microchip, the world of computing was a world of giants. Computers were hulking machines that occupied entire rooms, their walls lined with racks of glowing fragile vacuum tubes. These machines, like the ENIAC in the 1940s, were marvels of their time. They could perform calculations at speeds no human could match. But they were monstrous. They consumed enough power to light up a small town, generated immense heat, and were notoriously unreliable. A single vacuum tube, which acted as a switch, could burn out at any moment, bringing the entire calculation to a grinding halt. Finding the one faulty tube among 18,000 was a nightmare. The core problem wasn't just size or power consumption. It was a problem engineers called the tyranny of numbers. To make computers more powerful, you needed to add more components, more tubes, more resistors, more capacitors. But every new component had to be wired into the system by hand. More components meant more wires, more solder joints, more points of failure. The complexity grew exponentially. You would reach a point where the machine was so complex, it would be more likely to fail than to finish a calculation. Building a truly powerful and reliable computer seemed like a paradox. This wasn't just an academic problem. The Cold War was in full swing. The space race was beginning. The United States needed to build missile guidance systems and spacecraft computers. You couldn't put a room-sized, power-hungry, failure-prone ENIAC on top of a rocket. The military and NASA needed something powerful, but also small, lightweight, and, above all, reliable. The world desperately needed a way to escape the tyranny of numbers. The question wasn't just, how do we make transistors smaller? It was a more fundamental question. How do we get rid of the wires? The breakthrough came in the late 1950s with the invention of the integrated circuit. The idea, pursued independently by Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor, was revolutionary. What if, instead of making all the components separately and wiring them together, you could build them all at once, out of a single, solid piece of material? A monolithic idea. Noyce's version, which became the blueprint for the modern microchip, proposed carving all the components, the transistors, resistors, capacitors, and even the wires connecting them, out of a single sliver of silicon. This solved the tyranny of numbers. No more soldering, no more individual wires. Everything was integrated. It was a brilliant, world-changing concept, but it created a brand new and equally daunting problem. It's one thing to have the idea of carving a circuit into silicon. It's another thing entirely to actually do it. How do you sculpt a material with a pattern so small it can't be seen? What kind of chisel is fine enough for that work? The answer came from a seemingly unrelated field, printing, specifically from lithography, a process used for centuries to print images using a stone plate and ink. The core idea of lithography is to create a pattern on a surface where some areas accept ink and others repel it. The engineers at Fairchild Semiconductor, led by Robert Noyce, wondered if they could adapt this principle. What if, instead of using ink, they used light and chemicals? This was the birth of photolithography, the process that sits at the heart of all microchip manufacturing to this day. To understand it, let's use a simple analogy, making a custom t-shirt with a stencil. Imagine you want to put a complex design on a shirt. You wouldn't try to paint it freehand. You'd create a stencil. You lay the stencil over the shirt, you spray your paint, the paint goes through the cutout parts of the stencil, and when you lift it off, your design is left behind on the fabric. Photolithography is, at its core, the most advanced stenciling process ever invented. In this analogy, the t-shirt is our silicon wafer, a perfectly flat, perfectly round disk of pure silicon that will eventually be diced up into hundreds of individual chips. The paint is a special chemical called a photoresist, which has a peculiar property. It changes its chemical structure when exposed to light, and the stencil is called a mask or a photomask, which is a quartz plate that has the pattern of one layer of the circuit printed on it with an opaque material like chrome. So here's the basic process. You take your silicon wafer. You add a layer of the material you want to shape. Let's say a layer of silicon dioxide, which acts as an insulator. Then you coat the whole thing with a thin, even layer of the light-sensitive photoresist. Now comes the stencil. You place the mask just above the wafer and shine a powerful beam of ultraviolet light through it. Where the mask is transparent, the light passes through and hits the photoresist, hardening it like glue. Where the mask is opaque, the photoresist is shielded and remains soft and soluble. After the exposure, you wash the wafer in a solvent. The unhardened photoresist washes away, exposing the layer of silicon dioxide underneath it, perfectly matching the pattern from the mask. Now you have a wafer where some parts of the insulating layer are protected by hardened photoresist, and other parts are exposed. The final step is the chisel. You bathe the entire wafer in a hot corrosive gas. This gas eats away or etches the exposed silicon dioxide, but it can't touch the parts protected by the hardened photoresist. When the etching is done, you clean off the remaining hardened resist, and what are you left with? The layer of silicon dioxide has been permanently carved into the exact pattern from your stencil. You have just sculpted your first layer. The first critical question that challenges the magic is this. That's one layer, but a chip is a complex 3D structure. How do you build a skyscraper with a stencil? The answer is, you do it again, and again, and again, hundreds of times. Microchip manufacturing isn't one process, it's a relentless cycle of layering and sculpting, building up the chip's architecture floor by floor. The real story of how a chip is made begins not with a flash of light in a clean room, but with something far more humble, a grain of sand. The journey from a beach to the brain of your phone is a story of purification and perfection. Silicon is the second most abundant element in the Earth's crust, usually found as silicon dioxide, the main component of sand and quartz. But for our purposes, common sand won't do. We need silicon that is almost unbelievably pure. The standard for semiconductor manufacturing is 99.9999999% purity. That's called 99 silicon. For every billion silicon atoms, there can be only one single impurity atom. Why? Because a microchip is an electrical landscape. Billions of electrons are constantly racing along pathways, and a single stray atom of, say, boron or aluminum would be like a giant boulder in the middle of a freeway, causing electrical chaos. Getting to this level of purity is a massive industrial process involving furnaces heated to thousands of degrees and complex chemical reactions. Once we have this ultra-pure polysilicon, the next step is to give it a perfect structure. The silicon atoms in this purified material are arranged randomly, like a pile of marbles. For electricity to flow smoothly and predictably, the atoms need to be arranged in a perfect, repeating crystalline lattice. It needs to be a single crystal. To achieve this, the polysilicon is melted in a crucible. A tiny seed crystal with the desired perfect atomic structure is lowered into the molten silicon and then slowly, painstakingly pulled upwards while rotating. As it rises, the molten silicon cools and solidifies around the seed, inheriting its perfect crystal structure. The result is a massive single-crystal silicon cylinder called an ingot. These ingots can be over 6 feet long, weigh hundreds of pounds, and are more perfect in their atomic structure than the finest gemstone. They are a triumph of materials science. This perfect ingot is then sliced into thin discs using a diamond-tipped saw. These discs are polished until they are astronomically flat and mirror-smooth. Any bump or valley, even one just a few atoms high, could ruin the entire chip. These are the silicon wafers, the canvas upon which the most complex artworks in human history will be created. A single wafer, about the size of a dinner plate, will eventually hold hundreds of individual chips or dies. Now we enter the clean room. The air in a semiconductor fabrication plant, or fab, is thousands of times cleaner than the air in a surgical operating room. A single speck of dust is a giant, chip-killing meteor. Workers wear head-to-toe bunny suits to prevent any contamination. It's in this sterile environment that the real dance begins, the repetitive cycle of photolithography. Let's walk through it one more time, because this is the engine of the digital age. The process is often summarized as a loop: deposit, expose, etch. First, deposition. A new layer of material is deposited onto the entire surface of the wafer. This could be an insulating layer of silicon dioxide, a conductive layer of polysilicon to form a transistor's gate, or a metal layer like copper to create the wiring. These layers are often just a few atoms thick, laid down with incredible precision. Next, the wafer is coated with photoresist and moved into the lithography machine, or stepper. This is the most critical and expensive piece of equipment in the entire fab, costing over $100 million. Inside, a system of massive perfect lenses shrinks the pattern from the mask down and focuses it onto a small section of the wafer. The machine exposes one section, then steps to the next, exposing it with the same pattern until the entire wafer is covered. Then the solvent wash develops the pattern, leaving the hardened resist behind. Then comes the etch. This is the moment of sculpting. There are two main types. Wet etching uses liquid chemicals, but for modern fine features, they use dry etching. This involves creating a plasma, a superheated ionized gas, and using an electromagnetic field to shoot ions down onto the wafer like a subatomic sandblaster. This process carves out the unprotected material with vertical precision, creating the sharp, well-defined walls needed for modern transistors. After the etch, the remaining photoresist is stripped away, and the cycle begins again. A new layer is deposited, a new mask is used, a new pattern is exposed and etched. Layer by layer, mask by mask, the intricate three-dimensional city of transistors is built up. Some layers create the base of the transistors. Other layers, called interconnects, are the wiring, a dense multi-level highway system of copper wires that connects the billions of transistors to each other. A modern chip can have over 100 layers, each one perfectly aligned with the one below it. The entire process for a single wafer, from start to finish, can take over 2 months and involve more than 1,000 individual steps. It's here we can address a common misconception. People often use the word printed to describe how chips are made, while the term photolithography itself contains a reference to printing. It's fundamentally misleading. Printing is an additive process. You add ink to a page. Chip manufacturing is primarily a subtractive process. You start with a complete layer of material blanketing the entire wafer, and you carve away the parts you don't want. It is far more accurate to think of it not as printing, but as sculpture, a digital chisel, chipping away at layers of silicon to reveal the circuit hidden within. But as the decades passed and Moore's law demanded ever smaller transistors, engineers ran headfirst into what seemed like an unbreakable law of physics. The components they needed to sculpt were becoming smaller than the wavelength of the light they were using as their chisel. This should not be possible. It's a fundamental principle of optics called the diffraction limit. It states that you cannot use light to create a feature that is smaller than its own wavelength. Imagine trying to paint a tiny, delicate watercolor painting, but your only tool is a giant floppy paintbrush from a hardware store. No matter how steady your hand is, the smallest mark you can make is limited by the size of your brush. The light, as it passes through the small openings in the mask, diffracts. It spreads out, like a ripple in a pond. For decades, the light used in photolithography was deep ultraviolet light, or DUV, with a wavelength of 193 nanometers. By the early 2000s, engineers needed to create transistors with features smaller than 90 nanometers. Soon after, they were aiming for 45 nanometers, then 22, and today we are in the single digits. How could they possibly carve a 10 nanometer line with a 193 nanometer beam of light? It seemed like the end of the road for Moore's law. The industry was facing a wall, and the solution they found is the deepest, most surprising, aha moment in this entire story. It is the unseen giant that makes the modern world possible. The problem was light itself. The 193 nanometer wavelength of deep ultraviolet light was the most practical and stable light source available. Developing a reliable light source with a significantly shorter wavelength was proving to be a monumental challenge that would take decades to solve. So, with their light source fixed, the engineers had to get clever. They couldn't change their chisel, so they had to find a way to make it behave as if it were smaller. The breakthrough came from two ingenious, almost unbelievable tricks. The first trick is called immersion lithography. The idea was proposed by a Taiwanese engineer named Bern J. Lin. He realized that the wavelength of light isn't a fixed property. It changes depending on the medium it's traveling through. We've all seen this effect. A straw in a glass of water looks bent. An object at the bottom of a pool looks closer than it is. That's because light slows down and bends when it enters water. Critically, as it slows down, its effective wavelength shortens. So, Lin proposed something that sounded crazy at the time. What if you placed a drop of ultrapure water between the final lens of the lithography machine and the silicon wafer itself? By filling that tiny gap with water, the 193 nanometer light, as it passed through the water to hit the photoresist, would behave as if it had a much shorter wavelength, around 134 nanometers. It was a brilliant hack. It didn't change the light source, it changed the environment the light traveled through at the last, most critical moment. It was like giving your big paintbrush a magically finer tip, just as it touched the canvas. Implementing this was an immense engineering challenge, requiring perfectly pure, bubble-free water, and a system that could move at high speed without sloshing it around. But they did it. Immersion lithography squeezed another decade of life out of Moore's law, allowing the industry to shrink features down well below what the diffraction limit in air would have allowed. But even that wasn't enough. To get to the sizes of transistors we have today, mere nanometers across, they needed another even more mind-bending trick. This is where we enter the realm of computational lithography. The engineers accepted a simple fact. No matter what they did, the light was going to diffract and blur. A perfect square on the mask would not produce a perfect square on the wafer. It would produce a fuzzy, rounded blob. So they asked a profound question. What if we stop fighting the blur and instead learn to predict it perfectly? Using massive supercomputer clusters, they built sophisticated software models that could simulate exactly how the light would bend, spread, and interfere with itself as it passed through a given mask pattern. They could predict the exact shape of the blurry mess that would result. And once they could do that, they could do the opposite. They could work backward. They could ask the computer, to get the perfect crisp circuit shape we want on the wafer, what twisted, bizarre, nonsensical shape do we need to put on the mask? The results are astounding. A modern photomask doesn't look like the circuit it's designed to create. Straight lines on the desired circuit become strange, wavy patterns on the mask. Sharp corners become weird hook-like shapes. The mask is intentionally and precisely pre-distorted. it's a calculated mess. But when the 193 nanometer light shines through this warped funhouse mirror stencil, the inevitable blurring and diffraction processes magically resolve themselves. The distorted light waves interfere with each other in just the right way so that the image that lands on the wafer is the perfect, crisp, impossibly small circuit they wanted all along. This is the unseen giant. It's not just about lenses and light sources anymore. It's about software. It's about using immense computational power to master the physics of light, to bend the rules of optics, and to sculpt with a calculated pre-distorted blur. We are no longer just stenciling. We are using mathematics to tell light how to draw. This is how we cheat the laws of physics and continue to build the impossible. So, let's step back. We began with a seemingly magical piece of glass and metal. We end with the fundamental truths that make it possible. We start with the most common of materials, sand, and embark on a journey of extreme purification to create a perfect, man-made crystal. We then take that perfect canvas and build upon it, layer by layer, in the cleanest rooms on Earth. The core of this creation story is a simple principle, borrowed from the ancient art of printing, using a stencil to create a pattern. But we've taken that principle and pushed it to an unimaginable extreme. Our stencil is a plate of perfect quartz. Our ink is a beam of deep ultraviolet light. And our chisel is a stream of ionized gas, carving features billions of times smaller than the original stone carvings that gave lithography its name. The journey of the microchip shows us that innovation is often not about discovering a brand new law of physics, but about pushing the known laws to their absolute breaking point. When light itself seemed to impose a fundamental limit, engineers didn't give up. They cheated. They put a drop of water in the way. They used supercomputers to pre-warp their stencils, turning the very blurriness of light from an obstacle into a tool. Understanding this process matters because it demystifies the digital world. The cloud is not a cloud. It's a physical place, full of servers running on chips that were sculpted from silicon. The weightless world of information rests on a foundation of the most intense, precise, and material manufacturing ever conceived by humankind. It reminds us that at the heart of our most advanced technology, you won't find magic. You'll find chemistry, physics, and a relentless, almost absurd, human ingenuity. Every swipe, every tap, every thought you entrust to your devices is made possible not by code alone, but by a beam of light, a drop of water, and a perfectly grown crystal of common sand.
You've been listening to First Principles. Until next time, stay curious.